Okay, this is a continuation from class of the backside of the note sheet from day one of radicals, expressions, and rational exponents. We did A, B, and C in class, so I'm going to continue with question D. We're trying to simplify these radicals. And the way I was approaching this in class was I taught you how to write this in exponential form and then to simplify it that way. So we're going to continue with that idea. The first thing you want to do is you want to split D into two radicals. You want to write it as the third root of 54 times the third root of x to the fifth. Now, you might be thinking to yourself, there's nothing times itself 3 times that gives you 54. That's a nice number, and you'd be right. But anytime you have an index of 3, you're going to be looking for perfect squares. Excuse me, not perfect squares. You're going to be looking for perfect cubes. You're going to be looking things for like 2 to the third power, which is an 8. So if you can find a factor of 8, this is going to simplify nicely. Or 3 to the third, which is 27. If you can find a 27 in 54, you're going to be able to pull that out. Another perfect cube would be 4 to the third, which would give you 64. Obviously, there's not going to be a 64 easily divided into 54, so that's out. So let's try to look at this. If I divide 54 by 8, you get a number, but it's not a great one. Let's try. If I take 54 and I divide it by 8. Oh, I grabbed a calculator that's broken. (54) divided by 8. Doesn't work. So I can take 54 and try to divide 27 into it. It does work. It goes in twice. So you can break this down into the third root of 27 times 2, because 2 times 27 is 54. And what's nice now is you do know what the third root of 27 is. That's just 3. So when you take the third root of 27, you write a 3 down. You still have a third root of 2 left over. We can't do anything with that. It's reduced as far as it goes. Now what you learned in class is that the third root of x to the fifth can be written as x, where it has a new exponent. And that exponent is going to have a 5 in the numerator and a 3 in the denominator. The index of 3 becomes the denominator of the exponent. We also went over in class how you can rewrite this into nice whole numbers. So for example, 3 goes into 5 just one time. So this would be x to the 1 2/3 power, which is equal to, I'm going to write it below, it's the same thing as x to the first power, I'm not going to write the 1, it's implied, times x to the 2/3 power. We're almost done. Since on this worksheet we're trying to write things in radical form, simplified as far as possible, we need to keep going with this exponent here of 2/3. We're going to actually use the exponent and radical rule to go backwards. We're going to use the index of 3, the cube root, and this 2 to rewrite this x. It's going to become the third root of x squared. Everything else stays the same, and this is the final answer. So that's times x times the third root of 2 times 3, and that's the entire answer. Okay. Let's use the rule of radicals, the quotient rule, that allows us to separate on D the radicals. So this could be written as the third root of x to the 12th over the third root of 125. Now, in the prior page, I was writing down perfect cubes, and we were trying to find ones that went into 64 nicely, or 54 nicely. Well, this time we've got 125, and we want to find a perfect cube that goes into it. So I'm going to start listing those out again. 3 cubed is 27. 27 doesn't work. 4 cubed is 64. That doesn't work. 5 cubed is 125. Oh, that's going to work perfect. So we could rewrite this. At the very least, we know the denominator is actually a 5. 125 is a perfect cube. Now, the numerator, let's rewrite this in exponential form. It's going to be x to the 12 over 3 power. 12 over 3 nicely reduces to 4. So the final answer is x to the 4th over 5. All right, let's go to E. I'm going to separate these out just like I did the prior problem. I'm going to write this as the 4th root of x to the 16th times the 4th root of y to the 8th over the 4th root of 256. Now, if you're getting good at this, you're going to realize the 4th root of 16 is going to be whatever 16 divided by 4 is, which is 4. So this is going to be x to the 4th. And y to the 8th is the same thing, the 4th root of y to the 8th is the same thing as y raised to the 8 over 4 power, which is just y squared. Now this 4th root of 256, we got to look for 4th roots. So we got to think about what numbers time themselves would give us something that could divide nicely into 256. So I'm going to start listing some 4th roots, and then we're going to see if any of them divide nicely into 256. 2 to the 4th power is 16. And actually, that does go in nicely, but let's see if we can find a bigger one. 3 to the 4th power is going to be 81. I don't think that's going to work. 4 to the 4th power equals 256. Oh, happy day. We are lucky now. So the 4th root of 256 is 4. So that works out real nice. We're done there. F, we did in class. It was a lot of fun. Let's look at G. So this is going to be the 4th root of x to the 8th over the 4th root of 3. Numerator, we can figure that out pretty fast. It's just going to be x squared over the 4th root of 3. Now let's talk about rationalizing the denominator when you've got a 4th root. The goal is to get rid of the radical sign. The only way we can get rid of the radical sign when you have a 4th root is to have something that's a perfect 4th, meaning it's some number times itself 4 times that's really nice underneath the radical. Well, we pretty much have to make something up that'll be nice. So, for example, if we had 3 to the 4th power underneath the radical, I know that the 4th root of that is just 3. So we need to multiply by something so that when we take the 4th root of 3 times whatever that something is, you end up with the 4th root of 3 to the 4th. Because this simplifies nicely, we need it to simplify nicely. So we got to figure out what that thing is that we're going to multiply by to rationalize this denominator. Well, we need 3 to the 4th power. We have 3 to the 1st power. So to get 3 to the 4th power, we got to multiply by 3 more 3's. So I'm going to write the 4th root of 3 to the 3rd power. Because if you multiply these first 2 items, you're going to end up with our goal, a perfect 4th, 3 to the 4th. Because you have 3 to the 1st power times 3 to the 3rd power, which when you add those exponents, you get this 4. So we're getting a little messy up here. So I'm going to rewrite what we have, and then I'm going to write what we're going to multiply by to get rid of that radical in the denominator. So we have x squared over the fourth root of 3. We're going to multiply by the fourth root of 3 to the third power over the fourth root of 3 to the third power. When you do this, nothing simplifies in the numerator, but if you really like, you could take 3 to the third power and write it as 27. So this would be x squared, might as well make it in blue. That would be x squared times the fourth root of 27 over 3. And now we've rationalized the denominator. We simplified everything as far as you can. That would be the answer.